So the topic today is the Legendre polynomials, and as with the Chebyshev polynomials, we are going to restrict our attention to just the interval from -1 to 1. So that means we'll be working in the vector space of all functions defined on the interval from -1 to 1, and we'll be interested in projecting those functions onto the subspace of polynomials defined on that interval from -1 to 1. In particular, we'll be focusing on polynomials of degree up to n, which I'll denote by p sub n, right? So that'll be the subspace of polynomials of degree up to n. Now we're going to want to be able to project an arbitrary function from the space V of all smooth functions. And by the way, by smooth, I mean it has a sufficient number of derivatives, right? So typically we'll assume that if we're projecting the function onto Pn, we'll assume that it has n plus 1 continuous derivatives, right? So I'm leaving that a little bit vague, but we'll always assume it has enough continuous derivatives. We want to project a smooth function onto Pn, and then the first thing we have to do, as we saw in the last video, is to come up with an orthonormal basis for Pn, and then we can just project the function onto each element of the orthonormal basis and sum them. The orthonormal basis that we will come up with are called the Legendre polynomials, right? So that's the meaning of the Legendre polynomials. They're an orthonormal basis for the space of polynomial functions. So let's start small. Let's start with P0, the space of polynomials of degree 0, which are, of course, the constants, right? So these are just constant polynomials. This is a one-dimensional vector subspace. They're all generated by any single constant, any single non-zero constant, right, under linear combination. So to choose a basis element for a one-dimensional space, we just pick one element, and we want it to be an orthonormal basis. So in this case, that means that we have to choose a polynomial p of x equals some constant c, such that the magnitude of this polynomial, considered as a vector in this vector space, is 1. Well, the square of the magnitude is equal to p dotted with itself, which would be the integral of p times p on the interval from -1 to 1. And we want that to be equal to 1. So you integrate this function. P is just a constant, so we're just integrating the constant c squared. The integral from -1 to 1 is 2c squared. Setting this equal to 1 gives us that c has to be equal to 1 over radical 2. So we've got our basis element for P0. It's the constant polynomial E0 of x equals 1 over radical 2. Instead of using E as a notation for the basis elements, I'll use L0 and L1, L2, etc. So I'll write it this way. I'll say that the first basis element, L0 of x, is the constant polynomial 1 over radical 2. Okay, let's do an example. We'll actually calculate the projection of a function onto P0. So first I'll do it with the sine function. So the sine function on the interval from -1 to 1 looks like this, right? And the strategy is we'll calculate the dot product with L0, because L0 is a unit vector. The dot product will be enough to give us the projection, basically. So first we compute the dot product. The dot product of the sine function with L0, well, that's the integral of the sine function times 1 over radical 2. Pull out the 1 over radical 2, the integral of sine is minus cosine, and then when you evaluate this between -1 and 1, you get 0. We should have been able to predict that because sine is an odd function, right? So it's symmetric about the y-axis. If you integrate the sine function times any constant on the interval from -1 to 1, you're going to get 0, right? So okay, so the dot product is 0. So in a sense, sine is orthogonal to L0. That means that the projection of sine onto L0 is the dot product 0 times L0, which is just 0. Okay, so it's kind of disappointing. It turns out that the projection of the sine function onto P0 is just the zero polynomial. Okay, let's try it with cosine. Maybe we'll get something a tiny bit more interesting if we do it with cosine. So here's the cosine function on the interval from -1 to 1. It is an even function, and in this case, cosine is always positive on both the left and the right side of the interval from -1 to 1. So the dot product is not going to be 0 this time. Okay, so let's compute that. The dot product of cosine dotted with L0. So the integral cosine x times 1 over radical 2, integrated from -1 to 1. And so the antiderivative cosine is sine, and we evaluate it. We end up with, well, what happens is we get a sine of 1 minus sine of -1. Sine of -1 is minus sine 1. Those two negatives cancel, so we end up with 2 copies of sine divided by radical 2. 2 cancels against the radical 2 and leaves me with radical 2 sine 1. Now, that's the dot product. That's a number, right? Sine 1 is some slightly, well, irrational number, but it's just a number. And therefore, the projection of the cosine function onto L0 is the dot product, radical 2 sine 1 times L0. We recall that L0 itself is just a constant 1 over radical 2, so the radical 2's cancel, and the projection turns out to be simply the constant sine 1, which is about 8.41. So that's the closest constant function to the cosine function on the interval from -1 to 1. The constant function p of x equals 0.841. Now, there's less going on here than meets the eye, right? This is one of those cases where things are actually simpler than they look. All we've actually done here in computing these projections is we've computed the average value of the function. So the average value of the sine function on the interval from -1 to 1 is 0, and that's what we got for the projection. The average value of the cosine function is a little less obvious, but it turns out that, yes, the average value of the cosine function on this interval is exactly 0.841, equal to sine 1. And the reason that this projection ends up being simply the average value is, well, look at what we did. We took the integral of f, in our case it was either sine or cosine, but it could be any function, so whatever function we're doing, we take the integral of f times 1 over radical 2, which is L0, and then that gives us the dot product, and then we multiply that by L0, which is just 1 over radical 2. Well, pull the constant out, combine it with this radical 2, we're just taking 1/2 times the integral of f on the interval from -1 to 1. That is exactly the average value of f on that interval of length 2. So, computing the projection onto the constant function, or the space of constant polynomials, is exactly equivalent to simply computing the average value of the function. So now let's look at the subspace P1. This is the subspace of polynomials up to degree 1. So these are the functions of the form y equals mx plus b, right? In high school, you called these linear functions because the graph is a straight line. However, in mathematics, we call them affine functions. They're called linear only if the b parameter happens to be 0. Right? So P1 is the space of affine functions, mx plus b, or up to first degree polynomials. Now, we can reuse our L0 function as a part of our basis, right? So we'll reuse L0, and then we want to add another function, which I'll call L1, so that L1 together with L0 will make up a basis for P1. Now, we'll use the Gram-Schmidt process. So in the Gram-Schmidt process, what you want to do is you want to start with any basis for your subspace, and then you turn it into a orthonormal basis by applying this Gram-Schmidt algorithm, right? So for our basis, we'll take L0, 1 over radical 2, and we can take any really first degree polynomial. We may as well take the easiest one. Why don't we just take x? So I'm going to call that one v1 of x. That's like our first basis vector, right, after the constant basis vector. So these two functions together generate the whole space of affine functions under a linear combination. right? So by taking linear combinations of these two, we can get any affine function. The problem is these two functions may not be orthonormal, so we'll apply the Gram-Schmidt process. Now, we do know that this one, L0, is already normalized. It already has magnitude 1, so we can skip that step. The next step in the Gram-Schmidt process was to subtract the projection of V1 onto L0, right, onto the first basis vector. So we want to take V1 and subtract its projection onto the first basis vector so that all that's left is a vector which we'll call W1, which is orthogonal to the first basis vector. Okay, so that's the first step. So we have to compute this dot product V1 times dotted with L0. So in that case, it's going to be the integral from -1 to 1 of the V1 function, which is x, times the L0 function, which is just a constant 1 over radical 2. Okay, so this is an easy integral to do. You get the antiderivative x squared over 2 times radical 2, evaluated between -1 and 1, you end up with 0. In fact, you may as well note now that if you integrate any odd function, any function whose values on negative x values is exactly the negative of the values on positive x values, the integral of such a function on the interval from -1 to 1 is always 0, because the negative half will cancel the positive half, right? In particular, if you have an odd degree polynomial or an odd power monomial like this is just x to the first, then the integral is going to be 0. So, word to the wise, whenever you see we're taking an integral of an odd power of x, that's going to cancel, right? At least if we're doing it as we will be with Legendre polynomials, if we're taking the integral from -1 to 1, the integral of any odd power of x will be 0. Okay, so we've established that the dot product is 0. In other words, it turns out that these two functions, 1 over radical 2 and x, they actually were orthogonal. However, we still have to adjust radical x so that it has unit length, right? When we subtract its projection, we still get x, but now we have to normalize x so that its magnitude is 1. Well, how do we compute the magnitude? Well, the magnitude squared is equal to the dot product with itself. In our case, W1 is just x. So we're integrating x squared from -1 to 1. The antiderivative is x cubed over 3. You evaluate it from -1 to 1, you get 2/3. Okay, here's another tip. Again, because we're integrating always in this topic, right, the topic of Legendre polynomials, we're always integrating from -1 to 1. The integral of any even power of x is always going to be 2 over the power plus 1. So in other words, when you integrate x to the 2n from -1 to 1, you're always going to get 2 over 2n plus 1. Okay, so that means integrating polynomials is a complete piece of cake on this interval, right? And integrating monomials, x to any power, half of them are 0, the other half are very simple. They're just 2 over the power plus 1. Okay, so in our case, we wound up with W1 magnitude squared is equal to 2/3. So the magnitude of W1 is the square root of 2/3. And now finally what we do is to normalize W1, we take W1 divide by the magnitude of W1, so that's going to be the reciprocal, radical 3/2 times x. Right? And that'll be our L1. So that'll be our second Legendre polynomial. L1 equals radical 3/2 times x. It's a unit vector polynomial, and it's orthogonal to L0. So L0 and this L1 form an orthonormal basis for P1. Okay, let's do another example. Let's project a function now onto P1. This time I'll use the exponential function, so f of x equals e to the x. And remember, the procedure is when you want to project onto a subspace and you happen to have an orthonormal basis for the subspace, all you have to do is project onto each basis vector and then sum those projections. So okay, so first we'll project onto L0, and to do that, again, because L0 is a unit vector, the projection requires only that we calculate the dot product and then multiply the dot product times L0. So f dot L0, that's the integral from -1 to 1 of e to the x times 1 over radical 2. This is easy. I think I'll skip over some of these steps. So this is the exact value you come up with. It's about 1.66. Okay, so that's the dot product of the exponential function with L0. Remember that this is actually the average value of the exponential function on that interval from -1 to 1. Now we'll compute the dot product of f with L1. So this is going to be the integral from -1 to 1 of e to the x times radical 3/2 x. Now I can pull out the radical 3/2, but e to the x times x is going to require integration by parts. I kind of skipped over that. What you end up with is, the antiderivative is radical 3/2 times x e to the x minus e to the x, and then we have to evaluate that between -1 and 1, and you end up with radical 6 over e. Okay, you can check my arithmetic on that, but I think I did that correctly. Okay, so putting this together, we now know that the projection of our f onto P1 is the dot product with L0 times L0 plus the dot product with L1 times L1. Now, remembering that L0 is 1 over radical 2, the radical 2 times the radical 2 will give us 2 here in the denominator. And remembering that L1 was radical 3/2 times x, we get some cancellations. The radical 2 down here cancels the radical 2 from the radical 6, and then that'll leave us with radical 3 times radical 3. That gives us 3 divided by e. So this is what we get. This is our projection. It's a little messy, but if you crunch it down to numbers, it comes out to be about 1.10x plus 1.17. So that is the closest affine function to the exponential function, at least in the sense of L2 error, and when we restrict our attention to the interval from -1 to 1. So the projection is in orange here, right? That's our projection G, and the exponential function is the blue curve. So you can see it's not a bad approximation. I mean, there's a limit to how well you can approximate the exponential curve with a straight line, but this is the best way to do it, at least in the sense of L2 error. Okay, now let's keep going. Let's work out an orthonormal basis for P2. So this is the subspace of quadratic functions. Let me make that a little bigger. There we go. We have a jump start because we've already worked out L0 and L1, which are mutually orthogonal unit vectors that span the polynomials of degree up to 1. So all we have to do is add in x squared to that, and that is a basis that spans the quadratic functions. Right? Together with linear combination, these produce all the quadratic functions. So because we've already worked out L0 and L1, we really only have to apply the Gram-Schmidt process to x squared. So the first step is to take x squared and subtract off its projections onto L0 and L1. In order to do that, we have to work out the dot products. So we'll work out V2, which I'm calling x squared, right? I'm going to call x squared V2 of x. We'll have to work out the dot product of V2 with L0 and of V2 with L1. Well, this will be easy now. V2 dotted with L0, that's this integral, but here's the thing. We've got a constant of 1 over radical 2, and then we're integrating an even power of x, so we use our trick. We know the integral is going to be 2 over the power plus 1, so it's going to be 2/3. Okay, and this simplifies down to radical 2 over 3. The dot product of V2 with L1 is the integral of x squared times radical 3/2 times x. If you multiply these x's together, you get x to the 3rd power. That's an odd power, and we know that any odd power of x has an integral of 0, so that's going to come out to be 0. So now what we want to do is we're going to subtract from x squared, we're going to subtract off the projections onto L0 and L1, so that means we're going to form a new vector W2, which is equal to V2, minus the dot product with L0 times L0, minus the dot product with L1 times L1. Of course, this just cancels. Let's see, L0 is just 1 over radical 2. The radicals 2's cancel, so we just end up with x squared minus 1/3. So this is what I'm going to call W2. This is now orthogonal to both L0 and L1, but it is not yet normalized to have unit magnitude. So that's what we'll do next. So we compute its current magnitude. The magnitude squared of W2 is the integral of W2 times W2. So if you square W2, you get x to the fourth plus minus 2/3 x squared plus 1/9. So we're going to integrate this. Oops, I did it again. So we're going to integrate this guy here. And then again, we can use our trick. The integral of an even power of x is going to be 2 over the power plus 1. So the integral of x to the fourth is 2/5. We got a constant of negative 2/3 times the integral of x squared. That's going to be 2 over 3. And then we've got 1/9 integrated over an interval of length 2. That's going to be 1/9 times 2. So do the arithmetic. You find out that this is equal to 8 over 45. That's equal to the square of the magnitude. So the magnitude of W2 is the square root of this. And we take our W2, divide out the square root of 8 over radical 45. And I'll trust you guys to check my algebra here. But when you simplify the radicals and everything, it comes out to be this. 1/2 times radical 5/2 times the quantity 3x squared minus 1. So that is what we'll use as our L2. It's a unit vector polynomial, which is orthogonal to L0 and L1. So let's do another example, actually similar example. Let's again project the exponential function, but this time onto P2, this subspace of quadratic functions. Since we've already found the projection of the exponential function onto L0 and L1, all we really have to do that's new here is work out the projection onto L2. Okay, so to project the exponential function onto L2, we have to compute first the dot product with L2. So that's going to be the integral from -1 to 1 of the exponential function times L2 as we worked it out on the previous page. So L2 was this guy. Okay, now this one's getting a little bit messy here, but we can pull out the constants, and then we've got two terms in the integrand. E to the x is easy, but 3x squared e to the x, we have to integrate by parts twice to do that. I think I did that correctly. Correct me if I'm wrong. Double check my calculation, but I believe this is the antiderivative, and when you evaluate it between -1 and 1, you get this. Okay, so together with the dot products with L0 and L1 that we computed previously, we end up with a projection. We take the dot product times L0, the dot product times L1 times L1, the dot product times L2 times L2, and then adding everything up, we get this. So it looks like a bit of a mess, but if you crunch the numbers, you get this, and then if you add up like terms, you end up with approximately this. It's 0.537x squared plus 1.10x plus 0.99. And so that is approximately the quadratic function which best approximates the exponential function in the sense of L2 on the interval from -1 to 1. You really need all those qualifiers in there. This would not necessarily be a good approximation on any other interval, and it's not necessarily the best approximation in the sense of L infinity, in the sense of minimizing the worst case error. Right? Remember that the L2 error, you're kind of trying to minimize the total error at all places, and you're not necessarily minimizing the worst case error. Right? So that it's conceivable that here there may be bigger gaps between the two curves than there are with the, for example, using Chebyshev knots in order to form an interpolation. So here I've drawn the orange curve is the quadratic curve, the blue curve is the exponential curve. They're very, very close. But, you're not going to be able to get a great approximation just using a quadratic function. Okay, a note on notation. You will find if you look Legendre Polynomials up in our textbook or in a reference book, if you look it up on Wikipedia, they're given a little differently. First of all, they're denoted by P sub n, right? P for polynomial instead of L for Legendre. So this is how they're usually denoted. And also, more importantly, they're not normalized to have unit magnitude. They're given so that P sub n of 1 is always equal to 1, and also so that the square of the magnitude of P sub n is always 2 over 2n plus 1. Right? So in other words, they're normalized in a different way. They're not normalized to have unit magnitude. So for example, in the standard format, P0 of x is equal to 1, whereas I've given L0 of x equal to 1 over radical 2, so that it has unit magnitude. P1 of x in standard form is just x, whereas I've normalized it, so L1 of x is radical 3 over 2 times x, right? And so on. It's very easy to convert from one form to the other. My form, the form I've given, is the normalized form to have unit magnitude. So the normalized form is always equal to radical 2n plus 1 over 2 times the standard form. Right? That's just a very simple procedure for normalizing P sub n of x. Right? Here I've given the first 5 Legendre polynomials from P0 through P4 in both forms, standard form and normalized form. They're easy to find online. Wikipedia has a table of, I think, about 10 or so Legendre polynomials. So they're easy to look up when you need them. Also worth noting is that, as with the Chebyshev polynomials, there's a pattern here that the even-numbered Legendre polynomials are even polynomials. They only have even powers, and the odd-numbered Legendre polynomials have only odd powers of x. Right? So that pattern holds again. Okay, so suppose we want to do on MATLAB a calculation like we did in the examples earlier, projecting a function, like, for example, the exponential function. Let's use that again. Suppose we want to project it onto P4. Right? You don't really want to have to do all these calculations by hand, so you can actually do them all on MATLAB, of course. So first of all, what I've done here is I've copied all the coefficients from the previous page, right? All the coefficients of the normalized Legendre polynomials, and I've entered them as vectors in MATLAB here, right? Notice that I've made them all 5 vectors, right? Length 5 vectors, because that'll be easier to add them, combine them in various ways later. If you try to add a 3-vector plus a 4-vector, MATLAB will throw an error. So it's better just to make them all 5 vectors initially. So I filled them up with zeros at the end, as necessary. As I said, you can always look up the coefficients on Wikipedia or something. Also, I'm providing a function Legendre n, which takes as input a number n, and returns the coefficient for the nth Legendre polynomial in normalized form. So what I'm calling Ln of x. And so, for example, if you change your sim preferences so that floating point output is false, which I'd like to do in this case so I can see exact answers, right? Rather than seeing decimals, I'll see expressions written, in terms of square roots and things. Then, when you call Legendre n of 3, it'll give you a list of the coefficients for the third Legendre polynomial, that is L3 of x, here. And you'll see that this agrees with what we have over here for L3, right? We've got the square root of 7, and etc. Looks a little different, but it's equivalent. So you can use that also. Rather than looking them up, you can just use this to generate the coefficients. And then to make C3 a list of length 5, I just took the answer I just got and appended a 0 to it, which you can do very easily in MATLAB. I just said list answer comma 0. It just takes the previous answer and adds a 0 at the end. So this is exactly the same as what I had before, including the 0 I added at the end here. Right? So easy to do. So now what we have to do is find all the dot products with our function f, which is the exponential function, with all those basis vectors, the Li for going from 0 to 4. So I'll define di to be the dot product f dot li, which is the integral from -1 to 1 of e to the x times li of x. Now, later in the semester, we're going to talk about numerical integration. We're going to show how to use the computer to calculate numerical integrals, and we're going to do it starting from scratch. But MATLAB has a built-in integral command, which will do it for us, so I'm going to exploit that right now. So it computes estimates, very good estimates of integrals, right, numerically. So what we can do is we can compute these dot products using the integral command. So I'm going to say, so for example, d0 is going to be the integral of, and now the first input into the integral command is the integrand itself. Now, for some reason, I wrote them in a different order, but here what I've done is the blue box here contains L0 of x. I'm using the polyeval command to evaluate the polynomial that has the coefficient C0. Use your version, whatever you called your function that did that, right? That did the efficient algorithm for evaluating polynomials. And then I multiplied it times the exponential function, right? So that's the green box. And then, as the second and third inputs, you give the left and right endpoints for the limits of integration, right? So then I did that for each d, for d0 through d4, and we compute all these dot products. Now, next thing to do is to assemble all the projections into a single polynomial. So what I'm doing is I'm taking the dot product times c0. This basically corresponds to the dot product times the L0 polynomial, just represented by its coefficients, and then I add that with the dot product times C1, right, the coefficients for the L1 polynomial, and so on. So I add up the products of the dot products with the coefficients of the Legendre polynomials, and the total will be the coefficients of the projection. So CS here represents the coefficients of the projection of the exponential function onto the space, the subspace, P4 of polynomials up to degree 4. Now that we have these coefficients, we can plot it and we can compare the two curves. So I'm going to plot on the domain from -1 to 1, I'm going to plot the exponential function, that'll be the blue curve, and then polyeval with the c's and the x's, and with the starting point 0, right, with the center point 0. And that's going to be the second curve, which will be in orange, but you'll see that they're practically indistinguishable. So using a fourth degree polynomial produces a curve that's almost indistinguishable from the exponential function, at least on this interval from -1 to 1.